today we can finish our lecture, okay, for this semester, okay. And the final section for this, for the course is okay. We try to study the propagation of wave at the interface, okay. And as I mentioned before, okay, this problem relates to so-called hydrodynamic instability, okay. And so there's an additional course, okay. If you are interested, you can do hydrodynamics here. Okay. This is a complete course, okay? And talking about this. Okay. And here we just give you the kind of idea, okay, give you a test, okay, what's the hydrodynamic instability look like. And this is only one, okay, one partial part of the hydrodynamic instability. Okay. So here we, in the previous lecture, as I mentioned before, I introduced what's so-called the normal mode analysis, okay. And so this normal mode analysis is usually used, okay, try to test the system stability, okay. So we have a system, this is kind of control point of view. We have a system, and this system usually in hydrodynamic instability is the flow system, okay. And we like to test this system is stable or unstable, okay. And how do usually in control theory we test the system by using the perturbation, okay? And this is the idea. It looks like if you see the, okay, if you have a system like this, right? This is a ball, a small ball is inside this, okay? If you perturb this ball, okay, move away a little bit, and then release, this ball will be eventually back and forth and stay here. That's stable, right? This is kind of give a little bit perturbation, introduce a perturbation. Okay, inside this system, this is the starting mechanics part. Okay, this is the mechanics part, but this is fluid mechanics. However, if you vice versa, if you have a ball at this location, right, and then you introduce a little bit perturbation to here, what happens? Okay, instead of going back. Okay, so that's this system we call it stable. This system we call it unstable. Similar idea. Okay, we try to test the system by using perturbation. So we try to input a small perturbation into the system. Okay, and how do you describe small perturbation? Is one way to introduce a perturbation, okay, for this physical problem. We introduce a small amplitude wave. Okay, this epsilon is a very small amplitude wave, right? And then try to introduce at the interface. Okay, this is the interface. Okay, we try to introduce the small amplitude of the wave. This is and this wave is composed by cosine and sine function, right? Because as you can see, 2 pi over lambda x, right? This is give you the cosine 2 pi over lambda x plus sine 2 pi over lambda s. Okay, so that's a kind of using the Fourier transform Fourier series, okay? And use this kind of mode, okay? We call this mode, okay? And this mode usually all the sine cosine function represent the normal mode. Okay, they are independent with each other for the normal mode. So we introduce a very small perturbation, and this perturbation is superimposed by cosine and sine function here. Okay, and the clever thing here you have to remember. Instead, if you go back to the previous traveling wave, okay, if you go back to the traveling wave in the very beginning, okay. This is traveling wave, right? This traveling wave. Okay? And here we introduce a C, right? C is a real number because it's a wave speed, right? And in the normal mode analysis, instead of using the real number here, we introduce a sigma here. And sigma is a complex number. Okay, and sigma is including the real part and imaginary part. And real part is similar to the C we just before, right? C is the wave speed, so sigma r is the wave speed. Okay, it's like before. And only difference when you introduce the sigma is a complex number, this is wave speed. What's imaginary part is sigma I is what? Sigma I is okay. If you go through the analysis like this, okay, this is analysis. We try to introduce the sigma becomes sigma r plus I sigma I, right? According to the definition of sigma, is the real part plus the imaginary part. And if you kind of rearrange this equation, you can see here. If you know the small amplitude is potential I 2 pi over lambda x minus sigma RT. So this part is like a traveling wave, right? Traveling wave with a speed, wave speed sigma r. Okay, so this is a cosine sine function. It's a bounded function. Okay. However, as you can see here, this factor here. This factor here is potential 2 pi over lambda sigma IT here. And the sigma I, if the sigma I is what? Is greater than 0, whatever. Our small amplitude, initially small amplitude, will grow in with what? With time. And the sigma I is greater than 0. So amplitude will be close. So if you introduce a small amplitude here, this is small amplitude here. Okay? And then if the sigma I is greater than 0, whatever, this small amplitude, okay, input into the system, eventually this amplitude becomes epsilon times this. And sigma I is, if the system, after we check, for this system, sigma I is a hardly variable. And our small perturbation amplitude is potential growth with time. Right? Potential growth with time. So this small amplitude eventually for unstable will become like, once the output, okay, output will become like this. Okay. Like amplitudes increase, okay, growing with time. Okay. Vice versa, if the sigma I is less than 0, the sigma I less than 0, that's its potential mass with time, right? When time increases, this is negative. So that's become its potential decay. Okay? So it's potential decay because this system is stable. Sigma I is less than 0. Okay, its potential decay means if you have an amplitude, small amplitude, eventually will be by Acer. Okay, station amplitude will damping out. Okay? And so the system, the flow system, okay, could be unstable, could be stable. Okay, depending on what kind of, okay. And what's the application for this? What's the application for this? Sometimes we need a system is stable, sometimes we need a system is unstable. Not only we want the system unstable, okay. Sometimes we need the system stable, sometimes we need the system unstable. Okay, for example, okay, have you heard about so-called noise control? Noise control. What's the noise control mean? If you go to the, okay, any electronic store, okay, there's a company in the box, right? You know that. Okay, you generate the head, okay, the earphone, okay, and then they can cancel the noise, okay, the very expensive one, okay. So if you can cancel the noise, that means the flow will be noise is pressure, perturbation, pressure. So if you can cancel it, and this system make this noise disappear. And sometimes we need the system is unstable. Okay, like mixing. Okay, sometimes we have the mixing with two fluid. This is a fluid 1, this is fluid 2. And then if you have a fluid A and B, you want to mix together with the inside the flow. Okay? And this is the interface. This interface start to close. Okay? And then what happens? When they start to close, the chemical B and chemical A start to interact, right? And generate more interface, and eventually this can become so large, it become like this, merged together. Okay? And bring a lot of areas interaction due to unstable flow system. Okay. So here is just what we try to do. Okay, and this is the flow system. Okay, we try to introduce to you for this physical problem. We have two fluids. Okay, and this two fluid above we have a density low 2, velocity U2, and below we have the free stream velocity U1 and density low 1, right? And then this is the interface. Okay, and the interface. And we try to study, okay, for this kind of flow field or flow system, is it stable or unstable? Okay, and how to check the stable or unstable is depend on your sigma I, right? Imaginary part of sigma here. This is sigma, and we try to check the imaginary part of sigma I. Okay, and let's try to start to construct the Gabor equation for this flow system, because in this perturbation have to be input into this flow system. Okay, and how do you represent this flow system? We have to represent by the Gabor equation. Right? This always become mathematical. Okay, we try to introduce more perturbation into the flow system, and it's how to describe the flow system within the Gabor equation with a boundary condition. Right? And then to describe this flow system. And okay, again, chapter 6 here, we're using the velocity potential, right? There is a potential flow. So both of the fluid above is a phi 2. This is the velocity potential for the fluid above, and then fluid below the interface, our velocity potential is phi 1, for example. Okay, and we try to describe the whole system by using the velocity potential, and to describe this flow system. So here we kind of introduce a very special form of velocity potential. Here we introduce our U is equal to this. Okay, as I mentioned before. Okay, this is velocity potential. However, this is velocity potential is different from our previous velocity potential, right? Our previous velocity potential U is equal to gradient phi only. Okay, and here we know there's a free stream, right? We know there's a free stream U1 and U2 here, and this free stream, okay, is unaffected, okay, when the flow is away from this interface, right? When y is go to infinity or go a little far from this interface, the flow field will be always is U2 above, and flow field under here is always is U1 below, right? Only very close to the interface here, okay, very close to the interface here, we have velocity change, right? And this velocity change, we describe this velocity change near the interface here by this, as you can see here. Okay, so this is velocity potential represent the what? Represent the perturbation velocity potential. Perturbed by what? Perturbed by this interface. And this interface, as I show you, our interface initially is small perturbation, right? So this is a velocity potential due to I introduce a small perturbation at this interface to test this flow system. And this small perturbation on the interface cause the flow near the interface slightly change, okay, and the velocity potential change can be represented by this. Okay, so that's why we introduce our velocity like this. And because our velocity ui is represented as ui, capital Ui is potential ex direction. Okay, this is unit vector in acceleration plus a gradient phi I here. Okay, so our substantial derivative. Okay, this is representative of substantial derivative from our chapter 1. Remember, okay, and for this kind of interface problem in the chapter 6, there are not many, there are boundary conditions, right? The one of boundary condition we call the kinematic boundary condition. What's a kinematic boundary condition? The fluid particles on the interface is always on the interface. Okay, and that's represent at the beginning of our chapter here. If you go back to our very beginning of our chapter here, chapters, right? All the fluid particle, this is fluid particle, okay? On the interface is always on the interface, okay? So we have the dt, and how the interface can be represented. Y equal to eta is our interface, okay? So fluid particle at y equal to eta, means y minus eta. That's represent now the fluid particle on the interface. ddt of this fluid particle should be equal to 0. The physical meaning is what? The fluid particle on the interface, it didn't change with time. It's always the fluid particle only. So we have a sequence of fluid particle, a lot of fluid particle on the interface. All these fluid particles stay on the interface. Okay, that's so-called a kinematic, okay, condition, boundary condition. So you have to familiar with this, okay, when you deal with the free surface problem. Okay, and later, if you are interested, there are more and more, okay. And so we go back to our physical problem here. Okay, we try to introduce to you here. So our carbon equation, our kinematic boundary condition, right? Kinematic boundary condition is this I just mentioned. So I introduce this. Okay, this is ui. Once you introduce this, will be represented like this. Okay, and then my argument y minus eta will put here. Y minus eta, right? Y minus eta. Okay, and then you can, if you do that, I think I did that before, not here. Okay, I did a lot. You will eventually get this formula. Okay, get this formula. Once you evaluate this, you get this. Okay, and as you can see here, as phi I here is a small perturbation, right? It's a small velocity potential, okay, due to the perturbation. So this gradient phi is very small number, okay. And the gradient eta is what? Is our perturbation, right? This is our perturbation. It's also very small amplitude, or small, okay. So when there's small number times another small number, that becomes second order term, okay, and even smaller. So we can neglect this, the second order term here, okay. So our kinematic boundary condition reduced to this, okay, and you can write down is a partial phi I partial y is equal to partial eta partial t plus ui partial eta partial x, can be represented as here. Okay. And here this is a boundary condition at the interface. So it's y equal to 0 is our interface. Okay, y equal to 0 is our interface. So this is a kinematic boundary condition. Okay, you should be able to write it. Okay, the second boundary condition at the interface what is the dynamic boundary condition. Okay, and dynamic boundary condition is from what? From the Bernoulli equation. From Bernoulli equation. So this is Bernoulli equation. Okay, for unsteady. Okay. So we try to introduce this Bernoulli equation at the interface. Okay. As you can see here, okay, this constant give you the pressure, right? This constant give you the pressure. So later we can say, okay, this one, okay, is the okay. This is dynamic boundary condition. So we introduce, okay, dynamic boundary condition for our physical problem. And here ui dot ui, and ui should be represented by this. And I did that a little bit for you, right? This is ui dot ui, this is ui dot ui. So they give you the, okay, eventually give you this, okay? And this is ui dot ui squared, right? And then this is ui times gradient phi, okay? And then another is ui dot gradient phi, and this becomes 2 here, right? 2 times of the ui ex dot gradient phi, and plus this, okay, equal to this constant. Okay, and this is a acceleration vector, unit vector. So this only dot with only the acceleration has value. Otherwise, it's also is a ey or ez is also going with the ex, so that will equal to 0. So only time you can have a dot value is what inner dot value is a partial phi partial x. So we have this, okay, and eventually you. As you can see here, ui is a constant, right? I equal to 1 or I equal to 2 is a free string constant. Okay, free string above. So we can absorb this constant. We can move this constant to the right hand side equation here, and then give you another constant for each side. Okay, because I is equal to 1 or 2, right? And all equal to a constant. Okay. So let's give you the dynamic boundary condition here. Okay, I think I just did it here. Okay, for you, and then this one will be the same as this. Okay, so this is dynamic boundary condition from the Bernoulli equation. Okay, so we kind of control this flow system. Okay, the Gaussian equation we know is what? We know is the Laplace equation, right? Our phi should satisfy our Laplace equation. That's the potential flow Gaussian equation. Okay, and then okay, phi1 represent the flow underneath of the interface. Okay, below the interface. Phi2 represent the flow above the interface. So both phi1 and phi2 have to satisfy our Laplace equation for both sides. Okay, and at the interface here, we have to satisfy the kinematic boundary condition. Okay, and this is the kinetic boundary condition for phi1. Partial phi1 partial y is equal to this, and this is u1. Okay, and partial phi2 partial y is equal to this, and this is u2. This is our previous kinetic boundary condition, right? As you can see, I is equal to 1 here, and ui is equal to u1 here. So you get this formula. And when I equal to 2 here, and this ui, capital Ui equal to u2 here, it gives the second, okay, kinetic boundary condition for, okay, above the fluid and below the interface. Okay, so this is the kinetic boundary condition. And what's the dynamic boundary condition? Okay, dynamic boundary condition, as I said before, I show you that our dynamic boundary condition at the interface should reduce to this. Okay, should reduce to this. However, okay, since at the interface here, okay, this boundary condition give you the pressure, okay, so that at the interface of the either from above or from the below flow field, this is flow field, okay, and then if you evaluate the flow field from below the interface to at the interface, okay, I using the phi1 to evaluate this at the interface. Okay, and I also evaluate this our dynamic boundary condition phi2 from interface above flow field to evaluate this boundary condition at the interface. These two is on the same interface, right? On the same interface means what? They should be equal. Okay, so this interface constant should be equal to this interface constant. No matter you are evaluate by using the phi1 or phi2. Okay, so I just mentioned that if you're using the phi1 and try to evaluate the phi1 and try to find out what's the interface dynamic boundary condition, that's a pressure on the boundary on the interface. And also you can use in the phi2 to evaluate the pressure on the interface. These two pressures should be the same. Okay, these two pressures should be the same. Okay. So we kind of just finished our flow system, the complete set of flow system with a Gaussian equation, we have the boundary condition. Okay, and another boundary condition I think is much obvious. Okay, as you can see, our gradient phi I is finite and gradient phi 2 is finite. Okay, and also you can also from this you can also see, okay, because if you y approach to infinity, what happens? Y approach to infinity. When y approach to infinity, our partial phi 2 partial y is 1. This is our v velocity, right? V velocity, the far field above should be equal to what? 0. Because we know the flow field above, right? If we recover back to only the friction velocity U2, there is no y direction velocity. Right? Okay? When y go to mass infinity, you can conclude also your v partial phi 1 partial y is also equal to v. I think it's approach to 0 is much easier, right? Okay? Because what? When y go to mass infinity here, for example here, I know our free flow field only has a u1 is the x direction. Suppose there is no v direction velocity. Okay, when you far away from the interface, you should be able to get it. Right? Okay. So that's a kind of for far field. Okay, far field boundary condition. Far field boundary condition. Okay, so since we just described what does this flow system look like, so first thing I think when you deal with a hydrodynamic instability problem, you have to describe what the flow system look like. This flow system should be composed by what? Carbon equation with their boundary condition. Okay, and this is kind of the mathematically described or mathematically description of this flow system, right? By using the mathematical equation. Okay, so this flow system can be described by this set of the equation. Okay, so that's how beautiful mathematics can do, right? Everything become mathematics. Okay. Okay, so I think here is a kinetic boundary condition. Okay, and we have a dynamic boundary condition like this. Okay, so we describe the flow system kind of complete already. Okay. And next thing is what? Next thing we try to find out when I introduce a small perturbation. This is a small perturbation at the interface. I think what I did is I introduced this small perturbation into this flow system, right? At the interface, I kind of perturb a little bit by generating a small amplitude, this wave on the interface. Okay, and once I input this perturbation into this flow system, I would like to evaluate what happened after this flow system, after this perturbation, or after this interface perturbation, okay, small perturbation, okay, what happened after that, okay, and very similar to this, I perturb, right, I input this, and I perturb it, and I try to see is this will be go back to original position, and our amplitude will be decay, okay, it's potential decay. And all this, when I perturb this system here, this system will be eventually, okay, this amplitude will be growth, it's potentially, okay, and try to evaluate like this. Okay, so that's how we kind of using this as a test of this flow system, right? Try to test this flow system by small perturbation input into this flow system. Okay, next. Okay, once you input this perturbation at interface, we know how to do that already. Whatever, when you have the interface at the traveling, have a wave on the interface. Remember, in the beginning of this chapter, we try to deal with what? We try to deal with when I have a
small wave, okay, small amplitude wave, right? I have a small amplitude wave, okay. For example, here, from here, I have a small amplitude wave generated on the surface, and I try to evaluate the flow look like, right? This is the chapter